My name's Ghadi Shayban. It's a privilege to be here with familiar faces, unfamiliar faces, and it's amazing to see a room full of so many people here to see parsing. So parsing's not, yay! It's not typically like a super exciting subject, but I hope we're gonna spice it up today. We're gonna make parsing great again, and we're gonna do. We're going to have. We're going to take an idea from the history books, and we're going to bring it into Clojure, and we're going to see a library that I've written that employs this technique, which is kind of a unique technique for parsing. So before we start, just a little bit about who I am. I've been part of the Clojure community for, I think, 7 years now. I was at the first Clojure Conj. It's been a wild ride. I love this community so much. So many good ideas. Talking to everybody in the hall has been amazing. So here's to 7 more, 20 more. We'll see where we are. I'm also a pianist by training. I went to school for piano and conducting, and that's really been my background. And I switched to development pretty late in my life. I've worked on Clojure core, some of the internals, gave a talk on the compiler a couple conjs ago, was on the initial team for core async. So it's been a lot of fun. I work for a company now that's not doing Clojure. It's called PocketDoc. We're an API for health transactions. We provide connectivity to a lot of different insurance backends, and we sort of provide an adapter to 400 different insurance companies who speak different lingos, whose messages need to be all parsed differently. And we provide a lot of data APIs and curated data sets. And my colleague this morning gave me an encouraging note. So thank you, Colin. The internet is forever. Just remember that. He's a brilliant data scientist that works with us. So today the subject at hand is parsing. And we're going to take a really informal definition of parsing, and that is it's taking a flat stream of information, for example, in a file, and we're going to turn it into usually a structured set of information in memory. That's not your typical definition of parsing, but that's what I'm going to go with today because I designed a whole library around that very premise. The implementation that I take is a very old technique. It comes from 1971. It's a parsing machine. There's a lot of different ways of parsing. You can do regular expressions. You can do functional combinators. But a parsing machine is kind of one of the more esoteric and fun ways to do it. There's a few libraries that do it this way. Lua has a great one called LPEG. Google has one called RE2. JRuby has one called Joni, and I think that's based on a Ruby library that has the same technique. So that's the approach that I took, and I'm going to explain how it works from the high level to the very nitty-gritty. We're going to be looking at bytecode, so yay. So who here considers themselves a regex expert? Yeah. So what is this a terrible regex for? Email, yes, that's exactly right. So this is kind of terrible because it accepts dots everywhere, and I missed the repetition operator on the right-hand side, so that's something. So, what's that? It's very approximate. There's no underscores. This one is not battle tested. But the nice thing about regexes is they're generally pretty fast, but they can't express non-regular languages, anything that needs nesting. They can't express the complement very easily, like a string that doesn't contain a word, like if you had reserved words in a programming language. You need these ad hoc rules like the longest matching rule because they're inherently non-deterministic. Sometimes concatenating regexes isn't associative. The whole operator system in regexes is pretty ad hoc. There's laziness, there's repetition, there's possessive operators, you can be greedy, and there's not really a lot of formal semantics around it. There's not a formal performance model. There's a lot of pathological cases. There's a famous regex that you can look at that I think generally it looks okay, but it can take 27 seconds to parse out on a bad string. So regexes are pretty limited. They're so limited. I did some Googling. I love this. An email address regular expression that 99% works. It's like, and I found that there was a website that was like the maven of regexes. It was a whole library where you can just look at different regexes for different purposes. So if that doesn't impede your sleep at night, I don't know what will. This is a production quality email regex. So there's no abstraction capabilities in here. It's everything you like about string interfaces all in one string. So just to put it out there, the username is the top thing, then the ampersand is at the end, and the bottom is the domain, right? You can, if you squint, you can kind of see that. And then there's a lot of really subtle things, like the domain has these two groups on the bottom line that kind of look similar, but one of them doesn't have a dot at the end. So, like, imagine the mistakes debugging this thing, and the dot is there to handle not having two consecutive dots in a row. It's just wild. So there's a lot of subtleties going on here. It might as well be this certain language that my mom told me not to say on camera. So, so regexes, we're going to put those away for the remainder of the talk. Another approach is combinators. Combinators are really nice. It's the idea that you take a function and you build up more functions out of these little, you compose functions together to make more complicated functions. But each one of them has the signature of they take input and then they either produce a value and a remainder of input or they fail. So these are pretty nice. They're functional, but they're opaque black boxes. You can't look inside them to see what they're doing. You can't perform optimizations against a whole bunch of them. You can't do like a whole grammar analysis of what you're trying to parse and make more intelligent decisions. So we're also going to put those aside for the remainder of the talk. And just before we get like really started with this, I want to define a few words. And informally, we're going to say a grammar uses rules to describe a language. So formal terminology is usually oriented towards the generation of languages, not the recognition of languages. So that's generally where all the hierarchy, the language hierarchy comes around. There's the Chomsky hierarchy, and that involves a bunch of further restrictions. You have context-free, you have regular languages, and each one can has stricter rules, and they generate fewer types of languages. So today, the topic at hand is going to be parsing expression grammars. This is a type of grammar that sits in between regular grammars and context-free grammars. And I think it occupies kind of a sweet spot in terms of expressivity. So context-free grammars generate ambiguity. You can, depending on the rules, how you traverse the rules, you can end up with different parse trees. You can end up with a series of answers rather than exactly one answer. And parsing expression grammars have an additional constraint where you can't express both A and B at the same time. You never generate ambiguous parses. You always generate a deterministic parse. So the way they do this is they have an operator called ordered choice. Ordered choice says, so if you took the Yogi Berra quote about, if you encounter a fork in the road, take it, that's like a CFG. Pegs, if you encounter a fork in the road, always take the left one. That's what peg means. So in this rule, we're going to start with a little bit of notation. It means try to parse A. If A succeeds, the whole rule succeeds. Never parse B if A succeeds. If A fails, then attempt to parse B. So it's always biased toward the left side. This whole peg theory came around in 2002 with Brian Ford's thesis. So this is a relatively new idea. And even more than just this ordered choice operator, the emphasis of pegs is about recognition. It's about developing a parser, an algorithm for forming up what you're trying to parse, rather than trying to describe all the possible languages that your grammar can entail. So it's really a different mindset. Pegs are, you can almost call them practical expression grammars. You know, they're really they're biased towards recognizing the strings. Other features is that you don't need a separate scanner or lexer and the parser. You can do it all in one. So this is in line with the Clojure philosophy of constraints being generally good things. They lead to interesting designs. So we're going to focus on those, pegs with ordered choice. Okay? So let's go through, we're going to go through some semantics of pegs. We're going to go through the implementation of a library that uses pegs, and sort of the choices that I made along the way. So just to start off, there's really not a lot to this. You can match literals. So it could be a string that you're trying to match, or the character X. You can try to match classes of characters, like all the hex digits or all the alphanumerics. You can apply other rules, and this is sort of like calling another function to parse something else. So there's a, you know, it's sort of like a function call. And like I said, there's that ordered choice operator. Okay? Ordered choice is about resolving the ambiguity before it even happens. So this is really intentional. When you're writing the grammar, you specify what you're trying to parse first. That's the onus is on the grammar writer to do that. And CFGs can backtrack a lot. So they can backtrack, if they fail at some leaf rule, they can backtrack all the way up and try to do something else. But in pegs, the backtracking is strictly local. So when you're within a rule, you're never going to backtrack like outside of the scope of that rule. You're only going to backtrack locally. So that's kind of nice. But it has implications. You cannot do something like this, foo or foo bar. You can't try to parse a prefix first, because it'll always succeed on the prefix. It'll never match foo bar. So this is an invalid rule. Now, some of the peg libraries check for this. Mine doesn't, but you know that's sort of something you have to know when you're designing the grammars. You never try to parse the prefix first. So here's an example of doing repetition. This is if you want to match a C-style comment. So you start with the notation I'm going to use here is the rule is going to be on the left-hand side. Then there's going to be a left arrow, and the definition of the rule is on the right-hand side. I kind of like this. This notation's from the PEG paper, in that the left arrow means you're recognizing a rule, rather than usually the arrows go the other way, which means in CFGs, which means you're describing a language. So this is more oriented towards parsing. So this is how you loop. You try to match a starting comment followed by this close rule, and the close rule is going to be either, so you see the ordered choice operator, it's going to be either the end comment or dot, which is anything, followed by trying to reapply this close rule. So it sort of recursively chews through anything that isn't the end comment. So that's kind of like how you do a loop in a peg. Everybody with me so far? Okay, sweet. Similarly, this is how you search for something. Pegs always work in what's called anchored mode, so you're at a point in the input stream and you try to parse forward. It never sort of shifts by itself. If you wanted to search for foo within a long string, you do this. You make an ordered choice, so either foo or chew a character and then recursively try to apply the rule again. So sort of the variations on the previous slide. There's a couple other operators in PEG. There's these predicates. So these are for doing look-ahead. And is when you want to match a rule but not consume any input. So it kind of tries to apply something, and then if it succeeds, it will backtrack to the previous position and then try to do something else. So if we wanted to express the comments, you can use these predicates. Similarly, the not predicate does negative look ahead. I got those backwards. Whoops. So if you wanted to match a comment, you say start the comment, and then anything that isn't the end comment, repeated, followed by the end comment. Same thing, different way to express it. So those are extensions to the original PEG definition, but they're essential if you're trying to match anything with a PEG. They're essential to use those. Okay. We're going to move on to the implementation of an engine. So we said we're not going to use regular expressions. We're not going to use functional combinators. We're going to use something completely different. And this was really novel to me. I had been following Christophe Grand and his endeavors with parsing. He has a bunch of amazing Clojure libraries. There's one called seqexp, which is regular expressions over sequences. It's like 250 lines. It's the most beautiful code you've ever seen. It has a virtual machine in it. It has this macro-based assembly language. If there were an Oscar for like best Clojure library, this one's brilliant. But his endeavors sort of inspired me to look into this. And as I said, there's a few other libraries that do a virtual machine approach. And the basic idea is that you're going to compile your rules down into a set of instructions for a virtual machine to execute. And these are not going to be Java bytecode. These are going to be your own custom domain-specific bytecode that are exclusively oriented around parsing. Okay? They have nothing to do with Java bytecode, but how do we do this? We have to develop all the bytecodes. We have to define them. And so before you define the bytecode, you have to define what the machine's going to track. And that consists of 3 general areas. You need to keep track of where you are in the input stream, the position in the thing you're trying to chew. You need to keep track of the instruction that you're executing. And then you have this virtual stack of entries for calls and returns. And there's 2 types of stack entries, which we'll get into later, but just to foreshadow a little bit, one of them is going to be for general calls. That's the return address stack entry. And then the other one is when you want to backtrack. You're going to stick a little marker on the stack, and you're going to pop it off later when you need to backtrack. Okay. So that's the machine state. Then we have to design instructions. The instructions fall into 3 general categories. There's control flow. You can call things. You can return from rules. You can jump instructions, like just what do you call them? Unconditional branches, right? A jump. And then there are these 2 pair instructions called choice and commit. And those are the ones that are going to, they always come in pairs, and those are going to implement the ordered choice operator. There's a few more instructions around matching your input. You can match a character. You can match a set of characters. You can chew any character. And finally, parsing is just about recognizing, but you never really just want to recognize what you're parsing. You want to turn those into data structures. So you have to capture certain things. You have to take a fork and pick out the inputs. And so we have 2 special instructions that will put a lasso around what you want to capture. So that's the general design of the instruction types. And there's a wonderful paper by the author of the LPEG library, who's the creator of Lua, and he goes through the entire design of the Lua LPEG library. It's just a great paper. It's really, really accessible. I totally recommend it, and I read it several times while implementing this. So, but we have to first figure out how do we compile down our rules into the bytecode. So what we're going to do is we're going to take a bunch of rules, and we're going to just look at snippets, look at excerpts of bytecode streams to match certain things. So we're going to play like a little human compiler, okay? So I'm going to write the rule on the left-hand side, and then the instructions that describe it are going to be on the right. So this is the most simple thing. If you're just trying to match a string, you're going to emit 3 instructions. One's going to match F, one's going to match O, and one's going to match O. Straightforward, right? Okay, a little bit more sophisticated. If we wanted to match an open parentheses and then calling some rule A, and then a close parentheses, it's going to be also 3 instructions. You're going to match the parentheses, you're going to execute the call operation, then you're going to match the close parentheses. But what does the call operation do? It will save your address of it'll save the address of where you are, which is the call operation. It'll jump to this code for A. There's going to be some amount of bytecode instructions for A, and then it's going to end with a return, which will pop off that saved address and go back to the next instruction. Make sense? Yeah, okay. All right. And then if you want to parse a rule followed by another rule, it's really just going to be concatenating the bytecodes together. You're going to concatenate all the bytecode for A, you're going to splice it out, and then you're going to concatenate all the bytecode for B. So concatenation is exactly, concatenation of rules is concatenation of bytecode. All right. So we're going to ramp up the difficulty a little bit. And to soften the blow, I'm going to give you a picture of my dog, who's barely visible. And then we're going to linger a little bit. OK, so here's ordered choice. I'm going to introduce some new notation. We're going to have 2 labels. What the labels are going to do are we're going to refer to a position in the input stream. A position in the instruction stream. And some of the instructions are going to refer to these positions. The positions are symbolic right now, like LBL1, LBL2. But later, when we finish emitting all the bytecode out, we have to link those. They have to become not symbolic. They have to become absolute positions. So that's done at the very, very last step. You turn the labels into actual integers. OK, so this is where it gets fun. Ordered choice, you have to use these 2 instructions, choice and commit. What choice does is it says, remember this position so that you can come back to it later and backtrack. And what commit does is say the opposite. It says, forget that position. You don't need to remember that position to backtrack because you succeeded. We're just going to throw away that position. So, for example, if you wanted to match foo or bar, but prefer foo, what you're going to do is you're going to say choice label 1, which means remember the position label 1 as the backtrack entry. In case stuff goes sideways, jump to label 1. And then it's going to try to match F, then O, then O. If that succeeds, it's going to say, you know what, forget that backtrack entry, commit it, and jump to label 2, which is going to be the next instruction after all this stuff. In case you tried to match FOO and it failed, we're going to pop off that choice that we saved earlier, the label 1. We're going to jump directly to it, and then we're going to try to match BAR. OK? Make sense? So choice is about remembering. Commit is about forgetting. OK. So we can use choice to also represent optionality. You can try to match foo, and that's pretty simple. You remember the entry just after foo, and if in case foo fails, just jump to it directly. Make sense? Okay, now we're going to go to repetition. This is, again, a variation on the theme. This is another snippet. For repetition, try to match foo many times. You're going to remember the position right after what you're looping over. You're going to put that on the stack to maybe backtrack to. You're going to try to match foo. If that works, you're going to jump back up to the top and start again. So that commit really punts you back to label 1, and then you're going to try to do it again, and if the last time it's going to fail, and it's going to jump to the instruction immediately after this loop. Okay? So Some more complicated examples are going to come next. So you get a progressively cuter picture. This is my dog Mo. He's a mess. So here's how we do the not predicate. This is, we have to introduce a new instruction called fail, and that's just going to unconditionally fail. So what this does, this snippet starts by saving the current state using the label to. Then it's going to try to match A. If A succeeds, we're going to commit. We're going to throw away that thing that we remembered earlier, and we're going to jump to label 1. And label 1 is a landmine. It's fail. So what this means is basically if A matches, fail the whole thing, because we're trying to match not A. If A does not match, we're going to pop off that initial choice, the label 2, and jump directly to the code for B. Does that make sense? I've seen a lot of nods. That's good. All right. So that was probably the most complicated example. Everything else is derived from all the things that we've seen before, except capturing. So if I wanted to match A and also capture what I tried to parse, what we do is we put a begin and end around A. So this just uses the capture instructions. And there's a separate stack entirely in memory, and that just saves all the captures that you're accumulating. And so that's basically all there is to it. The original Lua LPEG paper has a lot of optimizations that you can do on the bytecode. So you can, if you try to match A or B or C with parentheses sort of grouped to the left, that's not going to be very efficient because it's going to keep backtracking out and trying the same thing over again. So what they do is they punt the associativity, they move it to the right, they say A or B or C. They just sort of shift it. The library that I wrote does implement the associativity optimization, but it doesn't implement the others yet. Tail calls are useful when you're trying to loop. If you try to match, you remember that searching example where you said A or eat a character and then recurse? When you recurse, you're going to want to do a tail call so you don't continually accumulate stack entries. Another optimization they do is what's called a head fail. This one's a little bit more complicated, but what it means is that if you try to match a rule that starts with a character, you have to do a call instruction and then try to match the character, and then that fails, and then you have to backtrack out. So what they do is they sort of move the matching of the character outside of the call, and they sort of pre-match, and that improves performance dramatically. I have not implemented this, but it's actually pretty straightforward. And finally, there's one last one where they optimize capturing. Just like in a head fail, if you consume a lot of stack entries, captures also consume stack entries. And if you try to capture something, you remember where you started capturing, and then you fail the match, you have to forget that. And so that causes churn on the stack. So what they do is they also sort of move the capturing, they delay it until later, until the last possible second. And all of these require just a tiny bit of analysis on the code. Okay, so the library I wrote was inspired directly by LPEG. LPEG is a really, really nice library. I'm going to show you a snippet of it that's pretty cool. But I didn't want the imperative approach that LPEG took. I wanted a more data structure approach. I wanted grammars to look exactly like a datomic query, so just a quoted map. That was what I wanted to, how I wanted to express the grammars. I also wanted the nice capture system that LPEG had, where you can not only capture regions of text, but you can also apply functions to the captures, which really simplifies parsing. And then I wanted to use the power of Clojure to do a macro system in the grammar, and I'll show you that later. But first, let's look at LPEG. I don't expect you to read all of this, but this is really cool. This is LPEG's using LPEG to match or to parse Unicode UTF-8, and the entire logic for it is is just in like 5 lines at the bottom. And so, so their notation's a little different. They use a crap ton of operator overloading. So their plus operator is actually the ordered choice slash operator in the peg that we saw earlier. And their slash operator is applying a function to a capture. So, so what they're saying here is, if you want to parse UTF-8, try to match a byte, call byte on it. Or, if that fails, try to match the 2-byte format. This, the .r is their like range of characters. So try to match that, followed by continuation byte, and then apply F2 if you succeed. And F2 is like just doing the decode logic. But it's really, really elegant. It's like a couple dozen lines, and this is just UTF-8. It's obviously right. It's just got all the nice properties. So I wanted something similar to this. LPEG is based on, they try to parse abstract bytes. I wanted to start at the character layer, so I already do the UTF-8 parsing into characters. So this is an example of the library that I wrote. This is parsing JSON. This is the entire JSON description in like 40 lines. This is the whole grammar. I'm not sure if zooming in will, I don't think zooming in will work. Maybe. But basically, it's a big quoted map. It has the name of the rule on the left-hand side and then the description of the rule on the right-hand side. How do you express the rules? Well, vectors mean concatenation. So at the top, you say JSON is either white space followed by a value. Or at the bottom, you could say, let's say the digits rule. That's one digit followed by another a set of repeating digits. So that's how you parse digits in JSON. So that vectors are sequencing or concatenation. Then anything inside of parentheses is going to be like a special form, just like in Lisp. So the slash operator is ordered choice. That follows the peg notation directly. So a JSON value is an ordered choice of a string, a number, an object, an array, JSON true, JSON false, or JSON null. And and then you just jump from each symbol to the rule that defines it. In this grammar, you don't have to like apply a function. You don't have to hug it with parentheses to apply it. You just refer to the symbol directly, and that jumps to the rule. I think that's about it. There's a couple other things I'm going to highlight a little later. The architecture of this library is exactly the architecture of a compiler. It starts with the grammar. You analyze the grammar. You produce an AST, which is just a bunch of nested maps. They kind of look like tools analyzer ASTs. Then a compiler takes the AST and emits a bunch of parsing bytecode. Then you take your input, the parsing bytecode, and then you need some implementations of these actions. So you kind of, the combination of the three becomes the input to the virtual machine, and then that does the parse. So this is like exactly a compiler architecture, same exact, same form. I wanted to have the AST in the middle because I wanted, if I went directly from the grammar to the bytecode, I couldn't do any of the code analysis for the optimizations. So that's why that part is critical. This is just a snippet from the virtual machine. I implemented the virtual machine in Java. Why? Because it just seemed appropriate that you're going to do a bunch of mutable things. It's just going to be a big switch statement. You're going to loop around, pop off an instruction, and try to execute it. And the switch statement just calls into the little helper methods. Here's an example helper method. If you wanted to match a character, get the instruction, find the character that you're referring to. If it matches, then bump up the PC, the program counter, move forward in the instructions stream, move forward in the subject stream, the input stream. Otherwise, fail. Here's a couple other examples. If you wanted to do the choice and commit, those pair instructions, basically make a new stack entry, remembering all the stuff that you need to remember, bump the stack up, bump the instruction to the next instruction, the PC, the program counter. Similarly, if you wanted to commit where you are, just discard the stack. Just move back one in the stack, and then jump back to the instruction that you're on. So that PC equals instruction PC, that means basically all of the instructions are just an integer array once they're all flattened out and linked, and you access the next element, and that becomes your return address, and you just jump directly to it, and then loop back up into the switch statement. So this was the first virtual machine that I wrote, and it was a lot of fun, but it took a long time to debug, and I realized why we value immutability in this community so much. But basically, the only thing worse than immutability, the only thing worse than mutability is implementing mutability. It was a disaster. Just implementing mutable state was just eye-opening. So back to the JSON grammar. When you match a rule, you want to take the things that you've captured, and sometimes you want to turn them into data structures. So I made these things called actions, and at the end of a rule, typically you put an action, and it transforms what you've captured into something in your domain. For example, if you matched true, false, or null at the end, the action that you want to do is to push a Boolean true onto the stack, not the string representation of true, which is what you captured. Similarly, if you're capturing like a JSON object, you want to take all the key values that you encountered along the way and reduce them into a Clojure map. On the flip side of it, if you want to describe the class of characters that you're matching, you want to express them symbolically. You don't want to say like that crazy regular expression string that nobody could parse. You want to just refer to a hex digit. You want to refer to an escaped character. You want to refer to white space symbolically and delay providing the implementation for that match until later. So that's what that is about the class business. The matchers and the actions, they're all described using an interface, so you can provide your own implementations. So for characters, it's just a simple match this Unicode code point. And I envision people implementing really efficient matchers. For example, if you're trying to match ASCII, you can match it using a bit mask really quickly, and you can, in some cases, match without branching. And so, lots of libraries don't do that right now. That is derived from Scala has a library called Parboiled, and they have these really nice character matchers in there. And so just a note, things that you do with if you're doing actions when you're trying to manipulate the captures that you've accumulated, you want to make sure that you do legit things. You can't pop too many elements beyond the stack frame. I'm exposing a mutable capture stack, so you have to be very careful that you don't buffer overflow your capture stack. There's a few different types of actions, pushing things, reducing your captures if you wanted to capture an array, or applying a function to the top of the capture stack. And so those are pretty clear. And like I said, the matching is a different interface that's pretty simple. You just, there's various little helpers to do matching. Just as a final example, I wanted to show how to match CSV. So this is an incomplete version of CSV. So a line of CSV is a record, and that consists of a field followed by a number of separators and then another field. And a field can be quoted or unquoted. I'm eliding all those definitions. And then the separator is just the comma. Okay? But you can see if you had this grammar description, you can turn a CSV matcher into a TSV matcher using a sock. You can just change that directly. That's not the goal of the library, but that's something that kind of falls out pretty nicely, where you can you can programmatically manipulate grammars. But that first line where it says field and then a separator followed by a field, that's a lot of boilerplate that comes up a lot. So you want a way to abstract it. You want a way to describe that idea of just repeating something with an interspersed separator. So there's a macro system in the grammar where you can take some boilerplatey looking thing and you can abstract it away using a macro. And so a macro is just a rule. It's like a higher order rule. It's a rule that takes in a rule and then it emits another rule. So in this case, I'm saying define me a macro called join, and it takes a field and a separator. And then here's the implementation for the macro. It takes a pattern and a separator, and it returns you a vector of pattern followed by a parenthesized star, then the separator and the pattern. So this is a really nice way of like building up or abstracting away a lot of boilerplate. Where this comes up a lot is in pegs, you really want to consume white space eagerly. Whenever you match a rule, try to eat as much white space behind it as possible. So you can write like a little white space macro that wraps another rule, and it just emits that rule followed by whatever choose white space in your grammar. So what I want to build for the So what I want to do to sort of finish out this library is I want to implement all the other analysis and optimizations in the original LPEG paper. I want to have them all there. And those really improve performance a lot. Performance is what kind of drove me to this approach in the first place. Virtual machines are super fast for doing this thing. The JSON grammar that I tried out, it's 99 lines of Clojure, and it performs within a factor of 5 of the Jackson JSON parser, which is like a hand-rolled 10,000 line custom Java recursive descent parser. It's nuts. But with a factor of 5, without much tuning, there's something to be said about like finding the right abstraction. I also want to build more character matchers, like maybe vectorized character matchers. I want to generalize the input so that you don't just match characters. You can match sequences, any abstract tokens. So that would be super useful in a lot of domains. And that's kind of what Christoph Grand's SeqX library does. It just parses sequences. I would also want to maybe use that to have a better interface for the whole capture system. I think exposing a mutable stack is maybe not necessarily the best way to do things, but I have to think a lot about that more. So anyway, just to recap, Clojure is stupidly powerful for doing this stuff. It's like a couple thousand lines of code, and you get a library that's like within 5 times the speed of a much larger library. I think it's really nice to use PEG systems because they're just a sweet spot in between regular expressions, which are just terrible to write, and much more complicated systems like full CFGs, where you have to know about ambiguity. You have to know how to resolve that stuff. And finally, it's been really rewarding to work on this library. But it's about the journey, not the destination. So if you have any questions, please ask me after in the hallway. Thank you so much.